Hi, I'm Katie Jameson. I'm going to talk about the Small Magellanic Cloud today, and in particular what we've learned from recent H1 observations from ASKAP and CO observations from ALMA. So I would first like to acknowledge the traditional owners of the land, the first Australians on which we meet, or at least I'm meeting on, and pay my respect to the elders of the Noongar people, past and present. So I like to give it all away at the beginning of the talk. So here's my quokka-sized version of this talk. So first I'll talk about why the SMC, why low mass galaxies are important, what it can tell us about star formation. Then I'll talk about what we know so far about the atomic and molecular gas in the Small Magellanic Cloud that we've learned from ASKAP observations and ALMA, particularly filaments everywhere. And then finally, I'll look towards the future of what's coming with GASKAP. So why the SMC? Well, it's my favorite galaxy. That doesn't mean it has to be yours, but I still think it's important regardless. So number one, it's really close, right? It's one of the nearest gas-rich star-forming galaxies. And so that means we can study it in high spatial resolution. And it's the only place outside of the Milky Way where we can really get into the details of the ISM. And that ISM is lower metallicity, which may have an effect on the way the galaxy forms stars. And then finally, it's low mass. And so it enters into a realm of parameter space where we really don't know that much about star formation because of the difficulty in observing these galaxies. And so I think that there are two really critical reasons understanding star formation in low mass galaxies is important. And the first is for understanding the epoch of reionization. And so here I'm showing you a simulation from Sphinx, and in the top left-hand corner, you're seeing the structure formation in the volume density of hydrogen, and in the bottom left, you're seeing the fractional ionization of hydrogen. And so what you can see from the structure formation is that the smaller scale structure will form first. So low mass galaxies will form first and will produce ionizing radiation from their stars. But if you get the star formation wrong in those low mass galaxies, your simulations of the epoch of reionization might not be quite accurate. So I think it's really critical that we know exactly how to model star formation in these simulations. Similarly, it's important to understand low mass galaxy star formation in the context of hierarchical galaxy evolution, right? So the idea being that lower mass galaxies will form first and create stellar masses, and then those will evolve into mergers and accumulations onto these larger galaxies. And so in here is showing a simulation from the lustrous TNG, a zoom in on the formation of a Milky Way-sized galaxy, and you see exactly that. And so again, if you get the star formation wrong in these low mass galaxies, it can affect the stellar masses that end up in the higher mass galaxies in the universe we see today. And so in the SMC and LMC, we're actually already seeing evidence that star formation may be proceeding differently. And so this comes from some previous work I've done where we estimate the total amount of molecular gas using a dust-based method. And from this, we think we have a good estimate of the total amount of molecular gas, the reservoir for fuel for star formation. And we can quantify exactly how it's forming stars by the molecular gas depletion time, which is just a ratio of the molecular gas to the star formation rate. And in both the SMC and Large Magellanic Cloud, the LMC, we find the depletion time is about half a gigayear. This is substantially less than the average 2 gigayears that's seen in more massive, high metallicity, nearby star-forming galaxies, which generally is the canonical value adopted and is used in some of these cosmological galaxy evolution simulations. Okay. So there's the background, but what do we know so far from our observations? Well, our H1 comes from GASKAP, which is the Galactic ASKAP survey, which is mapping the Milky Way and Magellanic system in OH and H1. And so here I'm showing you an all-sky image of H1 emission from previous surveys, and we have outlined the regions we plan to map as part of GASKAP. And so this includes the galactic plane, but then also large regions surrounding the whole Magellanic system. On the SMC and LMC, we plan to do very deep observations. And many of our first observations have been focused on the LMC or the SMC because it is small enough that it can fit within the 5 degree by 5 degree field of view of ASKAP. So that's nice and cute. And so you may have seen results from these first observations. Here is newest observation of the peak intensity of the H1 from our pilot phase 1 data. And so already we're seeing a lot of small scale structure and filaments, which I'll talk about next. So this is presenting work that's being done currently by Jackie Ma, who's just started as a postdoc at ANU. And the idea here is to characterize the filamentary structure using the rolling Hoff transform. And so here on the left, you're seeing an integrated intensity map of H1 over a given velocity channel. And the center is showing you that RHT output for the whole field. And the right is then showing you the distribution of angles of those different filamentary structures. And so here the idea is that one of the things that can be done is to look at if there are any consistent angles of the filaments that might indicate flows or consistent processes throughout the SMC. Okay, so what do we know about the molecular gas? This was our previously existing larger scale map of the molecular gas from CO emission from single disk observations. But then I thought, like, with the improved power of ALMA and what we saw in the targeted regions of surveys, I wanted to map a large scale region. So I did a 0.5 degree by 1 degree, which is this white dashed box in the southwest part of the bar. And this is what ALMA and the ACA, so the more compact array, can reveal. So this is 7 arcsecond resolution across 1 kiloparsec by 500 parsecs. And what it reveals is never before seen structures, lots of clumps of CO emission. And there's a lot of structures that seem like they could be large scale filaments, which is something I got very interested about. So to put this in a bit more of a context, the blue here is showing you the ionized gas, stage 2 regions from H alpha, and the green is showing you the dust emission from the Herschel 250 micron image. And here, if we just zoom in, this is kind of my new favorite area, and I think this has the potential to be a large filament. And so this whole structure, which may be kinetically related, could be up to 100 parsecs in length. So I've just started to compare the CO to the H1 and to the work that Jackie's been doing with the RHT. And so here we're showing integrated intensity maps for this velocity range where I see this large scale possible filament outlined in the blue box. And so the black contours here are showing you that peak intensity on the CO, and the white or the orange is showing you the integrated intensity of the H1, and the grayscale is showing you the results from the RHT of the filamentary structure. And what we see is that there is a correlation between the CO emission and peaks in the H1, but it seems to be a bit offset, and it's the same with the filaments traced by RHT. And so if we put it into 3 dimensions, here we're seeing the CO in red and the H1 in black. The idea here is we're looking at it kind of like a face-on projection, so it would be an integrated intensity. But if we play this, it will rotate up and you'll see the velocity dimension. And again, you'll see that the red is kind of offset from the peaks in the black and the H1. So it's offset spatially and in velocity. I'm not really sure what that means yet. So there's a bright future with GASKAP, clearly. We've already seen some really exciting results, but there's more data on the way. And so as part of phase 1, we have observation of the galactic plane, we have an observation of the galactic center, and we have these 3 fields of view around the SMC, including the stream and the bridge. And so this is a really exciting one, science by DS9, giving you some really fresh results, but putting together that stream field with the main body. And so we're really starting to see the sensitivity of the ASKAP's observations and the ability to pick up these really diffuse small scale features quite far away from the main body of the SMC. And then also, one thing that ASKAP, and in the future SKA will be super powerful for, is tracing the cold H1 through H1 absorption. And so here we're showing some results from James Dempsey with all of the different continuum sources you can pull out from the ASKAP image and look for absorption. And so of these 373 background sources, you can pull out absorption in 68 of them, so around 20%, and we get really great absorption spectra. So in the future, looking ahead, we're going to start, ASKAP is starting their pilot phase 2 observations the next couple months. We have decided to spend our 100 hours on 2 different fields in the LMC, including 30 Doradus. And so we'll get these really sensitive, high resolution H1 images for the first time to be able to explore even new environment. So that's the summary of my talk. We've seen really a lot of exciting new possibilities with H1 from ASKAP, which nicely complements this ALMA CO ACA observations. And we're really able to start to dig into the details, at least in the nearby galaxies, to better understand the transition of the gas from atomic to molecular and how that may affect star formation in low mass galaxies. Thank you.